Okay, just want to, I will try to be brief. I mean, the idea is just to, before we start the discussion, to say a few words on how this might connect to causal fermion systems. And this is joint work with Johannes Kleiner and Claudio. And the general message is that causal fermion systems naturally involve a stochastic background field. And moreover, the causal action principle is nonlinear. And putting these two things together, one gets in a natural way, or it's derived, a dynamical collapse theory, which is similar to the CSL model, which we saw yesterday in Lajos' talk, and which also Christian mentioned today, but there are a few differences. Okay, and the setup we are considering is quite similar to what Moritz showed us yesterday. So that's what we do, is we consider a causal fermion system in Minkowski space, like what Sebastian showed us in the school on Monday. And then we introduce an interaction, similar to what Patrick did. However, the interaction is not just a classical electromagnetic potential, but instead we allow for a non-local potential, for more general potential. So this is how this looks like. I see now the battery is low. Anyhow, maybe I can simply, does this work that you see it here? Yeah, okay, perfect. Okay, so this is like this non-local potential here, which can be written as an integral operator. And now just taking this very general ansatz, one can ask the question, are the linearized field equations still satisfied or not? And this gives constraints for the form of this potential. And the detailed analysis, which I spent quite a lot of time on that, is that the linearized field equations are satisfied if this integral has a specific form. So namely, it consists of given non-local kernels here and a number of potentials. And the number, capital N, is very large. I will say a bit more soon. So the upshot is, the homogeneous solution is not just homogeneous Maxwell, but there are many more homogeneous solutions, and this will be important for what follows. Good. So what does it mean non-local? On which scale? On one side, of course, there's the Planck scale. And then on the other side, there's the length scale of macroscopic physics, for example, the Fermi scale, Compton scale, if you like. And then now here we get another length scale, which you should think of as being somewhere in between. So there's still some freedom to play around with it. It's not really precisely known, but it's like a length scale which is somewhere in this range. And then the number of fields scales like this. So L min over epsilon is the same as the Planck length here. So therefore, it is typically a very large number simply because the Planck length is so small. And all these potentials satisfy the homogeneous wave equation. Okay, so that was a bit similar to what Christian showed us. I mean, now the particles and electron is surrounded by all these fields, which are then described stochastically. Okay, and now, I mean, I don't have time to really enter the details of this model, although this would be too much. I mean, just the idea is to give you a few, a few things we could discuss later. So the model we get has two important features. Also in contrast to what Christian and Lajos told us yesterday. Namely, what is important is that this stochastic field is non-local also in time. And this has a consequence for how conservation laws need to be formulated. Maybe you recall on Monday we had these surface layer integrals in Simone's talk. This is also what we need to do here. So the conservation law, in particular probability conservation, is formulated by a conserved surface layer integral. You can think of what integrates over a time strip, and the time width is this parameter L min. And working this out systematically really gives us an effective collapse model. And more recently, together with Claudio, we analyzed this more in detail. And it seems that the energy of the probe is conserved. So this means in contrast to what we saw this morning in Christian's talk. I mean, although the electron is in this path of stochastic fields, this does not lead to a heating of the probe, and therefore should also not lead to some gamma rays or photons which are emitted by the probe as a consequence of this collapse. Okay, and in fact, this is already all I wanted to tell you. I think maybe now we can directly go over to the discussion, and I think like Siddhant and Paula wanted to moderate this. Of course, unless of course if there are questions, I'm happy to answer also right now. Okay, sure, thanks.